So this problem says an object is removed from a room where the temperature is 65 degrees and is taken outside where the air temperature is 33 degrees. After 1 minute, the temperature of the object reads 56 degrees. What will be the temperature of the object at 2 minutes? Round your answer to 2 decimal places. So this is what we call Newton's law of cooling. And that says that the rate of change of the temperature over time is proportional to the difference between the temperature of the object and the surrounding temperature, which we call T sub A, or sometimes it's called S. So we use a negative sign here in front of the proportion constant just to make things nicer when we solve the equation. So here, big T is the temperature of the object, little t is time, T sub A is the temperature of the surrounding area. So what this means is, if there is a big difference between the temperature of the object and its surrounding temperature, then its temperature is going to change faster than if their temperatures were closer together, right? So if you bring a cup of coffee outside where it's cold outside, the coffee's going to cool down much faster than if you took it outside where it was really hot. Okay. All right. So we have some information here. So an object is removed from a room where the temperature is 65 degrees. So we're going to assume that that is our initial temperature of our object. So it was the temperature of the room, and then it was taken outside where the temperature is 33. So that T sub A is 33 degrees. After 1 minute, the temperature has dropped to 56 degrees. So the temperature of the object is going to move closer to the temperature of the surrounding, the air temperature. All right, so let's plug in T sub A, and then we'll have to just solve it from there. So T sub A is 33. So I'm going to get rid of the parentheses. And we can say this is a linear equation with respect to temperature. And we're going to just move this T to the left. So let's just call it T prime plus KT equals 33K. K is a constant. So that's a classic linear equation. We can use integrating factor e to the KT. Multiply that on both sides. This is little t here, and then big T. And that's going to be equal to 33K e to the KT. We'll reverse the product rule for derivatives. And then take the antiderivative of both sides. So here that just gets rid of the derivative. This is derivative with respect to little t. So here, since k is a constant, we'll divide by k. So the antiderivative of the right side will just be 33 e to the kt plus c. And then solve for t. We can multiply by e to the negative kt, and we'll get 33 plus c e to the negative kt. That's little t for time. So that's our function for the temperature of the object. But we have these two constants here, c and k. So we're going to use two initial values to solve for those. That's why we need two of them. We've got the initial temperature, it's 65 degrees, and then we have the temperature after 1 minute, it's 56 degrees. So we need both of those. So if you plug in the 0 first, that'll knock out the k because you'll be multiplying that by 0. And then you can just solve for c, and then you'll plug in the 1 next. to solve for the K. So I'm going to plug in 65 for the temperature, and then plug in 0 for the time. So e to the 0 is just 1. So I just get C. So here C is 65 minus 33. That's 32. All right, so now that's our C. And now we need to find the K. So we're going to plug in this initial value, T of 1 equals 56. So I'm going to plug in 56 for the temperature. And that's 33 plus 32, because I just found C, e to the negative K times 1. So that's just e to the negative K. All right, so 56 minus 33, that's going to be 23. And then divide both sides by 32. Then, to get rid of the e, when you've got what you want to solve for in the exponent, you can use natural log. So let's take natural log of both sides. That just leaves us with a negative K. And then multiply by negative 1. Then, well, actually, our function has negative K in there, so we can just plug this in for negative K. So I think that makes sense. We'll just do that. So we just need to plug that back in for negative K. So T of little t, right, that's going to be 33 plus 32 e to the natural log 23 over 32 t. And that is the same thing as, right, because these are multiplied, I can say, well, that's e to the natural log 23 over 32 all raised to the t. And now this e and natural log will cancel out. So this is 23 over 32 raised to the t. All right, so the original problem asks to find the temperature after 2 minutes. So we're just going to plug in 2 for little t. And then now I can approximate this. This is the final answer. And I get 49 point, it's said to round to 2 decimal places, so we'll say 49.53 degrees. So you can see that in the first minute, the temperature dropped 9 degrees, and now it's only dropped, 6.5 degrees. So it's going to get slower. The temperature drop is going to get slower as it gets closer to 33 degrees.